A spacecraft passes Earth at thousands of meters per second. Its path has been modelled for years. Newtonian gravity, relativistic correction, atmospheric drag, tidal effects, solar radiation pressure, even sunlight pushing on metal has a place in the calculation. This is not guesswork, it is orbital accounting. And then, at the end of the ledger, something remains. Not kilometers per second, not meters per second, only a few millimeters per second, about the speed of an ant. Small enough to look like noise, but large enough to trouble some of the most precise navigation models humans have ever built. This is the Flyby Anomaly, not a flash in the sky, not a strange light, not a witness report, just a small velocity residual hiding at the end of a nearly perfect calculation. And that is what makes it unsettling, because the anomaly appears in one of the most mature techniques humans have ever used to move through the solar system: gravity assist. A spacecraft approaches a planet. It falls into the planet's gravitational field. Its path bends, its direction changes, and it leaves with a new trajectory. Sometimes, relative to the Sun, it leaves with more useful speed. This is not magic. It is accounting. Energy, momentum, position, velocity, reference frames. Everything must balance, and most of the time it does. Voyager used gravity assists. Galileo used them. Cassini used them. Juno used them. For deep space missions, this is not a strange maneuver. It is standard navigation. But in a set of Earth flybys, researchers found something that did not fully close. Some spacecraft appear to leave Earth with a tiny outbound velocity residual. The most striking case was NEAR in 1998. The reported difference was about 13.46 millimeters per second. Rosetta in 2005 showed a smaller positive residual. Messenger in the same year showed little or no anomaly. At first, this sounds like a list of mission data, but the real puzzle is sharper. Rosetta returned to Earth again in 2007. The same spacecraft, the same planet, another gravity assist. But this time, the anomaly was not seen. The same spacecraft, a different path, a different geometry. That is why the Flyby anomaly is difficult. If the problem was simply a broken sensor, a leaking thruster, or a bad tracking system, we might expect a cleaner pattern. But the Flyby anomaly behaves as if the path itself matters, not only speed, orientation. Before reaching for new physics, the ordinary explanations must come first. Tracking noise, atmospheric drag, thermal recoil, tiny modelling errors, clock effects, communication effects, the uneven way sunlight and heat touch a spacecraft. This is where the Flyby anomaly must remain humble. A residual is not a discovery. A mismatch is not a revolution. The more careful statement is this. Under very high precision, some reported Earth flybys showed velocity residuals that were difficult to absorb into conventional modelling. That is all. But in science, that is all can still matter. Some small anomalies become revolutions. Mercury's perihelion precession helped point toward general relativity. The blackbody radiation problem helped open the door to quantum theory. But other anomalies become engineering corrections. The Pioneer anomaly, once mysterious, was later explained largely by uneven thermal radiation from the spacecraft itself. So the correct posture is not belief, and it is not dismissal. It is controlled suspicion. The Flyby anomaly becomes interesting because it asks a narrow question. Why do some paths through Earth's neighbourhood leave a residual, while others do not? One clue is geometry. The reported empirical pattern appears connected to the incoming direction of the spacecraft, the outgoing direction, and their relationship to Earth's equator. In other words, the question may not be simply, how fast was the spacecraft moving? It may be, through what geometric orientation did the spacecraft move? This is where PTQ enters, not as an answer, as a lens. PTQ stands for PT-symmetric quaternionic spacetime. It is a speculative geometric framework. Its central idea is that the physical world we observe may be only a projected sector of a deeper geometric structure. Imagine a shadow on a wall. The shadow is real, it can be measured, it has shape. But the object casting it may have more dimensions than the shadow can show. PTQ asks whether some physical residuals could appear when deeper geometry is forced into the observable spacetime sector. Not as magic, not as a hidden particle, but as projection residue. That phrase matters. Projection residue is not the observation itself. The observation is the velocity mismatch. Projection residue is an interpretation, a way of asking whether a small residual might come from the geometry of projection rather than from a new substance or a visible force. To understand the PT part, consider two operations. P means parity, a mirror reversal of space. T means time reversal, the direction of a process turned backward. A PT symmetric structure is one that remains stable under the combined transformation. In a visual metaphor, imagine a rotating geometric object and its mirror time counterpart. Most unstable distortions cancel. What remains is the part that can survive into observation. Then come quaternions. Ordinary numbers move along a line. Complex numbers rotate in a plane. Quaternions are a richer mathematical language for rotations, phases, and coupled orientations. For a spacecraft flyby, that matters because the anomaly may not depend only on speed. It may depend on orientation, on how the incoming path and outgoing path cut through a rotating background, on how that path relates to Earth's spin and equatorial geometry. In a PTQ-style interpretation, we can introduce a careful popular term, a geometric activator. This must be handled carefully. A geometric activator is not a particle. It is not a substance. It is not a hidden object. It is not something the spacecraft hits. It is a condition the trajectory satisfies. A way of asking, does this path activate a small correction in the projection geometry? Make it physical. Imagine Earth as a rotating sphere with an extremely fine grain. Most paths slide across the grain without leaving a mark, but a few paths cross the grain at a special angle. Nothing dramatic happens. No flash, no crack in space-time, no force you can point to. Only a tiny difference at the exit, a few millimeters per second. That is the metaphor. The scientific version would be much stricter. A PTQ-style model would have to define one correction term. Then it would have to keep that term fixed. No retuning for each mission. No choosing only the successful examples. The same term must face all cases. Why did NEAR show a strong positive residual? Why did Rosetta show a smaller one? Why did Messenger show almost none? And why did Rosetta appear anomalous in one Earth flyby, but not in another? That is the exam. A theory that explains only the anomaly is too easy. It must also explain the absence. This is why the Flyby Anomaly is more useful than many spectacular mysteries. It is numerical. It is historical. It is back-testable. Each flyby has a trajectory, an incoming direction, an outgoing direction, a perigee altitude, a velocity. The data are not perfect. The interpretation is not settled, but the target is sharp, millimeters per second. That is the difference between storytelling and science. If PTQ is only a metaphor, it remains philosophy. If PTQ can produce a fixed geometric correction that predicts when the residual appears, when it vanishes, and how large it should be, then it begins to become testable physics. That is the threshold. Not beauty, not mystery, prediction. The flyby anomaly may disappear. It may become another engineering correction, a better thermal model, a better tracking model, a better understanding of spacecraft surfaces and Earth's environment. That would still be science. But if a fixed geometric model can predict the sign, size, and absence of these residuals, then the anomaly becomes something more. Not proof, a test. Not a revelation, a target. A spacecraft does not need to tear open space-time. It only needs to pass through the right geometry. And for one brief moment, the universe may leave a number behind. A few millimeters per second. The smallest line in the ledger of gravity.